In this video, we are going to go over Chapter 3 and review it as you study for the exam. Chapter 3 is a smaller chunk of material compared to the previous chapters that we've done, Chapter 1 and then 2 and 10 together. But it deals with some concepts that'll lay the foundation for covalent bonding that we'll do next. And also we'll reuse this material. We'll lean on it again when we talk about solutions in Chapter 8 and colligative properties in Chapter 8. So even though it's shorter, it's very important. So I've kind of broken up how we're going to talk about this into a few different pieces here. Definitions, predicting charge, and then just talking about how ionic compounds form and going between names and chemical formulas. So first of all, the definition of an ionic compound is important. So it is going to be an electrostatic attraction between two different charges, between a cation and an anion. Your textbook says it is the transfer of an electron to another element, and that is not true. That is a redox reaction, and so this definition is the only definition that I'll accept as correct on things like exams. So heads up. So we've got our definition, and one thing that's important to also remember when we're defining this is that it will often be compared to covalent bonding and metallic bonding, which we won't cover in this class. But covalent bonding, by comparison, is going to be sharing electrons in a bond. And that'll be between two elements. And that sharing, which means like an electron spends time around two different nuclei, that sharing doesn't happen in our ionic bonding. We have electrons don't spend time in between the two atoms. It's just the charge that's positive being attracted to the negative charge, like opposites being attracted to one another. So that's our definition of ionic compounds we're going to use. Let's talk about kind of the foundational skill that we're going to need to be able to determine what ionic compounds will form. And that is predicting the charge of an element using just the periodic table. So the periodic table is going to help us predict charge for representative elements only. And these are going to be the first two. So the first two columns, or the first two groups. And it's going to be the last 6 groups of the periodic table. And remember, groups are the columns of elements that we have on our periodic table. And so this will connect to how we predict compounds for representative elements. And so it depends on if we're looking at a cation or an anion. Cation's a little bit simpler. When you have a cation, it's going to typically be a metal. So in this class, they'll always be metals. And we're going to say the group number will be equal to its charge. That's because we're going to assume for these cations that all of their valence electrons will be lost when they form a cation. And we know that the cation's group number will equal the number of valence electrons it has from Chapter 2. So if it's in group 1, it'll have a +1 charge. If it's group 2, it'll have a +2 charge. It might be worth highlighting that these are all positively charged. Now our anions are negatively charged, and they're going to be our nonmetals. So where our cations were our metals, these will typically be our nonmetals. And we'll calculate their charge based on the number of valence electrons they have, which is really the group number. So 8 minus the group number, or you can think of that as the number of valence electrons, will equal the charge. So for example, if it's in group 7, that means there's 7 valence electrons, right? So my charge would be 8 minus 7, that's 1. So my charge is -1 for that element. All right, now that we know how to predict charges, we're going to use that tool to help us determine the ratio that different elements will combine when they form an ionic compound. And let's start with the more straightforward version of this, the representative elements. I'm going to move this up a bit to give us a little bit more room. So within our representative elements, we're always going to combine things where we have our cation first and then our anion second. Our cation is always going to be our metal, and our anion will be our non-metal typically. And we're going to combine these in a ratio where the charges balance out when you add them together. And we can determine this by a little algebra or just comparing the two. Or what we can do is we can use the Criss-Cross Rule, which states that if I have a metal with a charge and an anion with a different charge, I can take the magnitude of that charge and make it the subscript of the opposite atom. So, for example, if we had a metal with a +3 charge and an anion with a -1 charge, we would use our Criss-Cross Rule to determine that I need 1 metal ion and 3 of my anions to form a balanced 0 charge compound. Right, now the kind of other component of this, we can go backwards, of course. We can take that chemical formula and do the reverse Criss-Cross Rule to determine what our charges are. So I would like everyone to be able to go from chemicals, or let's call these elements. How about this? I'd like everyone to be able to go from elements to compounds and both directions. Take the compound and determine what the element charges are, and then take the charges of elements that you know are combining and determine what the compound is. So you should be able to go either way. All right, now let's talk about naming conventions. Naming conventions are going to be somewhat straightforward for our ionic compounds. They get really complicated with some of our covalent compounds, but we're always going to name the cation. It's just element name, plus our anion element name will come second. And we're going to modify our anion element name to add an IDE ending. So if we had, actually let's do calcium and oxygen, I would just name the calcium its element name, which is calcium, space, and then oxygen will become oxide. And that IDE ending tells us that it's an anion, it has a negative charge. Now most of these concepts we just talked about for our representative elements will apply to the transition metals and the polyatomic ions. There's just going to be a few little curveballs along the way with those too. So let's start with transition metals. Transition metals happen, they're the subset of elements that fall in between the second or the first 2 and the last 6 of our groups of elements on our periodic table. They actually even look like indented down. Our transition metals can have lots of different charges. So just knowing where it is on the periodic table won't help you predict what its charge is, like we were able to do with our representative elements. So this means that we have to figure out what that charge is based on what it's bonded to. And so this means we'll have to problem solve the charge from the anion. When we name these, we are going to have to give people information about it. Iron chloride could be lots of different compounds. It can have 1, 2, 3, 4, 5 different chlorine atoms ionically bonded to that iron. And so when we name these, we're always going to put the charge in Roman numerals after the metal name. So we'll have the metal name, then in parentheses we'll have the charge, and then we'll have our anion name. And this will have to be in Roman numerals. Now let's focus on polyatomic ions. So these ones are tricky in that they are covalently bonded compounds that have an overall charge, and so they can participate in ionic bonds. And so it's more than one nonmetal will make a polyatomic ion. You can get the names and the charges from the polyatomic ion chart. You do not need to memorize these. And their names will be like carbonate, sulfate, phosphate, or hydroxide, things that will look different and not match up perfectly with our representative element naming system. Hydroxide is probably the closest one that sounds similar, but then if you look for hydroxygen or hydroxy in the periodic table, you won't find it. And so one of the tricks with these too is, so our naming conventions we'll have to go to the chart for, and their charges will be told to us, but we'll need to treat these as one unit. So if I need 2 carbonate ions to balance out an iron plus, or how about a manganese plus 4, then I'm going to write that as, well, manganese. And then I'll put parentheses around the carbonate ion and then the 2 following. So this tells me the number of carbonate units that I need to balance out my charge. And I make sure that my carbonate ion is the same chemical formula as it is on its own. So I can't change the subscripts in the actual ion. I have to treat it as one unit. And that summarizes, let's make that a little bigger. That summarizes chapter 3 in a nutshell.